Practice quiz problem number 1. Let me give you a minute with this. "30 seconds more. Okay. If this was y equals x squared, it would look like this. And the lowest height is 0, because whenever you square something, you're always going to get positive. So the very lowest output is 0. This one is also the case. It's something, because you have to do that in parentheses first. Something squared. Its lowest height is also going to be 0. Height is 0. But it'll occur not when x is 0 over here, but when x is 2. So you'd move over 2 to the right. And that's where you're going to get the lowest height. Either side of that, you're going to be going up. And this is totally consistent with what we know about when you replace the x with x minus 2, it causes a horizontal shift, replacing the x does. And it goes opposite the direction of sign. Horizontal positive direction is to the right, and it's appear to be to the left, but it's negative means go to the right in the horizontal world. Everything's opposite. And give me a little feedback on, were you able to get number 1? Okay. Because it's kind of a tricky concept. It's opposite direction, horizontal versus vertical. Alright, this is from yesterday. The equation for the speed, not the height, of a ball, which is thrown straight up in the air, is given by v for velocity, is 128 minus 32t. Where v is the velocity in feet per second, and t is the number of seconds after the ball is thrown. With what initial velocity was the ball thrown? And what is the meaning of the slope? So this is an equation, kind of like y equals mx plus b, and there's a slope in there, and and there's a y-intercept in there, and it's asking about those things. So let me give you a little bit of time with this. Another 30 seconds. Alright, so I'm going to pull out all my tricks. On tougher ones, I write the input variable and the output variable, but give a brief description. T is time in seconds, and V is the velocity, and it's in feet per second. And I might also, if I was really struggling with understanding this, make a T, which is in seconds, and V, which is in feet per seconds, chart. At time 0, I just plug in 0 for the T here, and I'm going to get 128. At time t equal 1, I plug it in here. 132 minus 32, I think that's going to be 96. And then another second later, 128 minus 32 times 2, subtract another 32 from there, you get 64. Okay. Now, with what initial velocity was the ball thrown? It's really asking, what's going on when we start? Initial velocity is 128 feet per second. When you start the experiment, or start the clock, the ball was thrown straight up in the air. And what's the meaning of the slope? The slope was a sentence that we had last time. Remember? Slope. When we first started this, we had all these ways that we did the slope. But the slope is the change in the output each time the input increases by 1. When you want to interpret it, that's what we want. So what it means is every time this goes up by 1, this goes down by 32. But we got to put this in nice, easy words a third grader would understand. Every second so every time t goes up by 1, a second passes. Every second, the velocity decreases by 32 feet per second. So what happens is you keep it, if you kept this thing going, at 3 seconds it would drop another 32 to 32. At 4 seconds it would be at 0. Now that would be the highest point. The velocity of the ball, how fast it's going upwards, it's getting slower and slower and slower because gravity keeps slowing it down. And then at the very top, it has a velocity, upward velocity of 0. And then it starts going down, and it's going to be negative 32. And it's going to get faster and faster going down. It still decreases by 32, like this. All right, give me feedback on number 2. And if English is your native language, these usually are a lot easier to understand. And it's an extra complication if it's also a language thing. Alright, let's go to this next one. Find 5 to the 0. And then 0 divided by 7. And then 3 divided by 0. Okay. 30 seconds more. Anything to the 0 power is 1. And it might seem crazy. I remember, why isn't it 5 times itself 0 times? And so why isn't it 0? Because remember, 5 to the 1, 5 to the 2, 5 to the 3. So this is repeated multiplication. When you're getting into these things, it's got to be repeated division eventually for the negative exponents. So it's dividing by 5. And you notice if you move down this way, you got to divide by 5. Divide by 5. Divide by 5. If you're moving up, you got to multiply by 5. So you move down, you got to divide by 5. And that's the transitioning point, and it's got to be 1, or else none of our math will work and be consistent. Alright, this one. I'm going to try 0. Suppose I've forgotten whether this is supposed to be 0 or undefined. Well, I'm just going to try 0. And then I'm going to check. Because I remember, like 8 divided by 2 is 4. I can check 2 times 4 is equal to 8. So 0 times 7 is equal to 0. Oh, it works. Let's try this one the same way. Does 0 times 0 equals 3? No way. This doesn't check. And if we think of the bigger definition, if the top number is bigger than the bottom number, we say how many times bigger is this than this? 8 divided by 2, you need 4 of these added together. Added 2 to itself 4 times to get 8. So it's how many times bigger the top number is than the bottom number. And how many times do you have to add 0 to itself to get the 3? Add to itself a million times and you're still stuck at 0. Alright. Give me a little feedback on these 3. Is this too basic, or is it helpful to review these periodically? consensus is, although people are getting it, it's still a good and helpful review. So I'll continue to put those kind of things in. All right, that's it for the practice quiz. Questions on homework or on anything else? So this modeling with linear function stuff, you guys were okay with that? That's kind of cool, because we were kind of rushing at the end. I wasn't 100% sure I'd gotten far enough. All right, if no questions, let's go to 5.2, power functions and polynomial functions. All right, kind of looking at where we've gone lately from the beginning of the course. We've kind of been jumping in various places in the book. We started with functions. What's a function? It has to pass the vertical line test, domain and range. Now, rates of change had a lot to do with slopes. And that was way back in 3.3, and that's, again, 4.2. It had a lot to do with slopes. Okay, and we had composition of functions, F little circle G, and then inverse functions, they went together. And then there was transformations of functions, which we reviewed, one of those in the practice quiz today. Exponents in scientific notation, radicals. Radicals and exponents can go back and forth. Radicals are the same as fractional exponents. Okay, rectangular coordinate system, we had distance formula and a midpoint formula. Other types of equations, those were mostly equations containing square roots. Okay, now power functions, polynomial functions. And we're doing a couple sections in chapter 5, but these are pretty important functions. Polynomial functions. All right. Before I get into what is a polynomial function and what's a power function, let me kind of set the stage of why we want this stuff. As one of the really powerful ways that we use math is to model data. We look at data and then we try to find equations that model it, and then we can kind of like try to predict things, maybe predict the future with it and so on. All right. Suppose you'd gathered a whole bunch of data and it told you years of education, years of education on this axis, and annual salary over here. So these are people with lower number of years of education, and these are people, you get way up here, people with graduate degrees. And then you had the annual salary, how much they made each year. And you get all these dots for all these data points, and it'll vary. And like this dot way up here and this dot way out here, we call those outliers. They don't kind of fit with the general, but there's always usually some outliers. But in general, there seems to be a trend. And could we use a linear function or a parabola to model this data? And the answer is, when the dots kind of form a pattern that looks like a line, yes. And there's a thing called the line of best fit. And there's actually, you can get a computer to draw the line and will go through the data just in the best possible way. And it'll go right through the heart of this data. And that line of best fit could then be used to predict, if you only had the data up to a certain number of years of education, you could predict out further and so on. Okay, and you could go in between values. if you had a function for this. And a computer can easily come up with that function as well. Alright, so the answer on this one is yes. So can you use a line, linear function, or a parabola to model? Now this one is, oops, I keep going backwards. Alright, class size versus learning. So, in the field of education, you might find the same school doing very different philosophies depending on who's in charge. They might get, somebody who's running a school who says, "Oh, learning best happens when there's small class sizes. So it's going to change all the class sizes to be as small as possible." And then that person retires and the new leader comes in and they say, doesn't matter what size the class is, we'll save a lot of money if we, bump the average class size up from 20 students to 30 students. And they can have lots of different philosophies. Well, suppose you actually go and test the research, and studies have been done. And different studies will probably come up with different results. And so the study came with, when the class size was small, there wasn't as much learning. When they tested how much were the students actually learning. When the class size were really big, they weren't learning so much. And it tended to hump like this. Then, in this situation, if this is what they find out, then a line does not model what happens. If it curves like this, you can't get a linear model like this. But you could get a parabola, and you could get a parabola of best fit. That would kind of run through the data like this. Now, parabolas are symmetric, so let me fix this one a little bit. You couldn't make it go follow the data quite so closely there. So you would have to arch down kind of like it was doing over here on this side. Okay. And but you could get some kind of model for the situation, a mathematical model for it. All right. Suppose a company is following its profits in certain years, and it goes up, down, back up. Now here, so yes, it's a parabola. And we saw, for instance, of a parabola over here. This would be a downward parabola that we would need, and we'd need to shift it over and up and so on. But we could do that. Now over here, we wouldn't be able to model this. It's not linear, and it's not a parabola. If it just had one hump, we could model it with a parabola. When it's got two humps, we also call these turning points. It turns from going uphill to downhill. Two turning points, we can't do it either way. But what we're going to find out today is that we could model this. Could be modeled. With a higher degree polynomial. Okay. So that's the stuff we're going to look into today. And polynomial terminology. So let's start out with what is a polynomial. An example of a polynomial is, now they have to have whole number exponents. So If you had like a negative or a fractional exponent, that's not a polynomial. They got to be really simple kind of things like this. They can't go into the negatives. And when you get down to one where it's like 3x squared plus 1, this is what we call the constant term. But sometimes we like to look at it as if it had an x to the 0 next to it. Because remember, then this fits kind of the pattern. Is if we wanted to see what are all the powers of x here, you could look at this function this way. 3x squared. Now there's no x to the first. You could think of it as its coefficient is 0. And then 1x to the 0. And now you can see the powers of x decrease by 1 every time. This usually isn't written as x to the 0, but it could be if we wanted to. And when you see a function like this, g of x equals 5, and somebody says, is that a polynomial? You can say, yes it is, and somebody else will say, hey, but it doesn't even have an x. But you can say, we can imagine that there's an x to the 0, like we did with this constant right over here. And so it would be a 0th degree polynomial. Now, and I notice I use this term degree of a polynomial. The degree is the highest power on your variable. So this one, f of x, is a 3rd degree polynomial. The highest power is 3, 3rd degree polynomial. This one is a 0th degree polynomial if you think it has x to the 0, if you think of it that way. Okay. If we didn't have this 5x cubed term, we'd say that this was a 2nd degree polynomial. Okay. Now, we love to have polynomials written in this order. The highest power of x first on down. So decreasing in the order of the powers of x. When you put it in that order, then the leading term is the first term. And the leading coefficient is the number in front of that first term. The leading coefficient would be 5. All right. Any questions? Okay. So let's go down to number 3. In behavior. What happens at the far end? So, we're going to be looking at polynomials in general, because the only ones we've looked at so far that we knew is 1st degree polynomials. Like this one might be something like this, like f of x equals, if it had a y-intercept of like 1 and a slope of like 1x plus 1. That's a 1st degree polynomial. That would produce this line. Okay. Here is a 2nd degree polynomial that would produce a parabola. But what about when they have more wiggles and stuff? Well, we got to learn about all that stuff so that we could model with polynomials. But the first big topic is in behavior. What happens at the far right and the far left of the graph? And to answer this question, what happens at the very, very far right? Now, I'm going to make this a little bit better here. I want it to look like it's getting closer and closer to the x-axis without touching it. Jumped on me. Like this. All right. So, how we would describe a graph like this, we'd say on the far right, the height of the graph gets closer and closer to the x-axis. And in this case, the x-axis is a horizontal asymptote. Horizontal asymptote is what it gets closer and closer to. So sometimes we show horizontal asymptotes with like a dotted line. But the dotted line would be right on top of this black line, so you wouldn't be able to see it. So I might extend it over here, showing that this gets closer and closer to this. Okay. On the far left, the height, or the output of the graph, is getting, well, the heights keep getting lower and lower and lower. No boundary. It doesn't like have a lower bound where if you tried to say, oh, it never get below this height, you'd always crash through whatever boundary you put. So we say it goes to negative infinity. So this is how we describe end behavior. All right. And we're going to show the end behavior of a few different graphs. The first one, y equals 3x plus 2. To show the end behavior of this, I am just going to do this. There's, on the far right, what's happening? Is it going way up or is it going way down? And on the far left, is it going way up or is it going way down? Or is it doing something not either one of those? Is it perhaps like going into closer and closer to the x-axis? Well, how do I decide among all these possibilities for this? Well, I know that this one has a y-intercept of 2. It has a slope of 3. So it would rise 3 and run 1. And so I'd be connecting. Now, the thing is I don't want this line. I don't really want the whole thing. I only want the end behavior. So if I want to show the end behavior only, you don't graph the whole function. You get rid of all this. The only thing you keep is on the far right, it's going up. Now look at, that's not even a very good representation of the steepness of which it goes. But it doesn't matter. You just want to show that to the far right, it's going up. And to the far left, this line would be going down. This is all you would show. To show the end behavior of this graph, you wouldn't even have this part. You would just have a quick sketch, and you'd have an arrow on the far right, going up, arrow on the far left, going down, and that would be your picture of the end behavior of this. All right, so let's see if you've got this idea now. Give me a quick sketch of the end behavior for B. And when you get your answer, type it into your group chat. And you can type it in by like this. Far right. And then you could say what it's doing. Going, closer and closer to the x-axis, or going up, or going down. Far left, what is it doing? Because you can't really do a picture into your group chat. You could do R and L for right and left. Okay, go ahead and hit enter when you have that. And group 6, what do you have on this? Are you there, group 6?
Yeah, sorry, I thought somebody else was going to be the spokesperson, but we have one of our group members saying it goes down 5 on the axis.
It goes down where?
It goes down 5 on the y-axis.
Goes down 5 on the y-axis, okay? And how does that affect my picture over here? And if you can add any more, you can answer. If you're not sure, that's fine.
Good, I
Yeah.
can answer.
Oh,
So what I had done is, I don't know if I'm correct or not, but I just went up. Went up 1 on
Okay.
the y-axis, and then I went. I don't know. Now looking at it now, I think I went down 5 on the y-axis.
1, 2, 3, 4, 5. Okay.
And then I plotted the point there at -5. So
Right
then
here?
there's 2.
Those
Yes,
2
sir.
points?
Yes, sir.
You're
But
really close.
not.
All right. You're really close. Let's do that. M is -5. What we do is we have to turn it into a fraction. So we make it -5 over 1. And this is the rise. And this is the run. So from here, y-intercept is 1. That was correct. Rise -5, you go down 5. That's correct. But what you're missing is then run 1. And so instead of making that point here, we make this other point down 5 over 1. And then we connect these 2 points with our line. Now, what does this tell me about the end behavior? We'd really get rid of all this. We'd say on the far right, it's going down. And on the far left, it's going up. So on the far right, it's down. On the far left, it's going up. That's the end behavior of this function. In the picture, we'd actually get rid of the real function. We just want to know the end behavior. Put all our focus on, does this go up or down on the far left and then on the far right. Okay. Go to the next one. So, the same question. Let me repeat the question. What happens? Show the end behavior. All right, so do a graph showing the end behavior only, and then put it into your group chat. And how you put it in your group chat, you might put it like, right. What's happening at the far right and what's happening at the far left. And go ahead and hit enter. And group 1, what do you have for the end behavior of this?
We got, let's see, I think it's L up and R up. So they both go up.
They're both going up? Okay, and who am I talking to?
Chrissy
Chrissy.
from
Okay,
group 1.
great. So we know the real curve is this. It's this parabola. But all we really have to draw is this and this. And we erase this when we're just focusing on the end behavior. We just want to know on the far right, it's going up or down? It's going up. And on the far left, what's it doing? It's also going up. Showing the end behavior. All right. Do part D. And type it into your group chat. "30 seconds more." All right, group 2. What do you have for the end behavior here?
For the right side, it goes down, and same for the left.
Down on both. All right, this is a downward shaping parabola. We know that, like when we did the reflections, the negative sign here caused it to reflect across the x-axis. So if we were just showing end behavior, we'd just show a picture like this. That's it. And when we get to x cubed, let me do these now. This one. I might show this much. When I put large positive numbers, like 10, I get 10 cubed, which is 1,000. I'm going to get, it's going to be going up. But if I put large negative numbers, it's still negative. So this, the outputs will be large negative, so it's going down. And when we go to y equals x to the 4th, the end behavior if you were taking 10, you'd get 1 with 4 zeros. It's clearly going up. But if you're taking negative inputs, when you take it to an even power, the negative happens 4 times, and they pair up, and all the negatives cancel out, and we still get the same thing. So this is also going up over here. All right. So there's only 4 possible choices for end behavior for polynomial functions. Now, the title of this was Power Functions and Polynomial Functions. When you have a simple one where it's just x to a power, this is called a power function. Just x to a power. There's nothing else on it. There's not plus 3x squared plus, you know, so if it's just x to a power, then it's called a power function. And power functions are really important to get the basic ideas about things down. We can find out a lot from the end behavior of power functions that'll transfer to big old polynomials in general. So there are only four choices of end behavior for polynomials. And they are way to the right, it's going up, and way to the left, it's going down. Where did I see something like this? This is when y equals like x cubed, when this is odd. Because when you take a negative input to an odd power, you still get a negative result. Now, you might get it like this, where on the far left, instead of going down, it goes up, and on the far right, it goes down instead of, so it's kind of the reverse of what this is. Can anybody tell me what would be an example that would do this kind of end behavior? Y equals, anybody can just interject.
Negative x cubed?
That's it. Just when you take the negative, it flips the whole world around. So now a positive 10 as an input is going to give you a negative 1,000 as an output. And a negative 10 as an input is going to give you a positive 1,000 as an output. All right. When they're both up, it's kind of like y equals x to the fourth, as long as that guy is even. The exponent is even. And then both down, it's like this, and that would happen like negative x to the fourth. It would still have to be even to make them both go in the same direction. But if it's negative, then they both have the end behavior going down. Alright, so we're going to pause here, and we will start again. At 1:33 p.m. And before I take my break, does anybody need to talk to me about anything? All right, we'll start up again. And we start with this question. Approximately how large is 1 million plus 1? So, a really brief 20 seconds. Type in your answer to your group chat, and I'm going to ask a group in a moment. All right, group 5. How large approximately is 1 million plus 1?
A million and one.
All right, that's the common response, because we can easily add these two together and get 1,000,001.
Approximately moment.
But yes, what we want to say though is, suppose it was like this. We say that there's this certain city that has 1,000,000 people in it. Now yesterday one more person moved in there. How many people are in the city? We wouldn't say it's 1,000,001. If we just meant it approximately, that there was 1,000,000, then when we add these together, we would just say that it's approximately 1,000,000. Okay, so approximately meaning kind of we're rounding off, and we're not getting precise, because if you went too precise, you'd kind of be implying the wrong thing, like you were actually counting every last person. It was an up-to-date number. We use approximations for lots of things when we want to report. We say that Earth is 93 million miles from the sun, and that approximation is good enough for most things. Now, let's go to the next one. When one number is 1,000,000 times larger, 1,000,000 times as large. When one number is 1,000,000 times as large as the other number, their sum is approximately the larger number. Now, how much larger is x to the 23rd than x to the 22nd when x is 1,000,000? Type that into your group chat. Hit enter. All right, group 2. What's the answer?
We said 1,000,000 larger.
Yes, it's 1,000,000 times larger. Now, when x is 1,000,000, x to the 22 has an incredible number of zeros in it. And x to the 23, it might have, like, I don't know, isn't there like 6 zeros, 6 times 20? It's more than 100 zeros, 1 with more than 100 zeros. And this is 1 with more than 100 zeros, but it's got 6 more zeros than this one has. That's the big thing. It's got an extra x in it. It's x times x to the 22. And so that x is 1,000,000, so it's 1,000,000 times larger. All right, when x is 1,000,000, x to the 22 plus x to the 23, under the same line of thinking we've been using, is approximately x to the 23. Even though that's only 1 unit digit, 1 unit bigger than this one, when x is 1,000,000, add these together, you get approximately the bigger one. All right. Now, what is the end behavior? And end behavior, remember, you draw a graph, and you say, what's happening on the far right? Does it go way up or way down? What far left? Way up, way down. What's the end behavior of this? From the line of thinking we've been using. I'll give you a minute and type your answer into your group chat. Excuse me. Okay, group 6. What do you have?
Okay, for this one, oh wait, hold on, who's our spokesperson? Listen. Left goes down.
Left goes down.
Yeah.
And what about right?
Goes up.
Goes up. And is this Landon?
Yeah.
And if you're just reading what other people, that's fine. But if you can you tell me why it goes up on the right?
I'm a little bit confused.
Okay. But thanks for reporting this. All right. It turns out that this, even though it's got a multiplier of 9, that is insignificant. When we're talking about way to the right on the x-axis, we mean way to the right. We mean even past when x is 1,000,000. Now when x is 1,000,000, this is more than 1,000,000 times bigger than this. So that even that number 9 is minuscule compared to this number being 1,000,000 times bigger than this number. Now, this wants it to be positive, because you take a large positive number to the 23rd power, you get a positive. This is trying to make this result negative, because it's got a minus sign in front of it. Which one's going to win the battle when these two are fighting it over? Well, this one, because it's 1,000,000 times as big when x is 1,000,000. When we mean end behavior, we mean even bigger than 1,000,000. We mean billions. Not even that. Trillions. Not even that. It's when x gets super, super large, this wins the battle. And so, when you're looking at end behavior and you're comparing the exponents, the only one that matters is the one with the highest degree. Even if this number was, instead of 9, it was 9,000, that's still minuscule compared to how big x gets to be when we're going way out to the right. So the whole answer is the same as this, and it's an odd with a positive coefficient. So on the right it's up, and on the left it's down. All right. So that has to do with the end behavior of this. It's kind of a complex explanation on this. We'll see how well you're understanding this as we go to more of these. Here are some from the textbook, and let me circle one of these. Let's all do number 21. Determine the end behavior of this one. So, right and left. I'll give you a minute. And type your answer into your group chat. Don't hit enter quite yet. I'll tell you when to hit enter. Go ahead and hit enter. Okay, group 5. What do you have for the end behavior of this?
Left down and right down.
Left down and right down. And am I speaking with Daniel?
Yeah.
Okay. And can you explain why, Daniel? If you can't, that's fine.
Um, uh, I think the polynomial is a degree of 4, and
Very good.
the slope is negative. So.
Very good. All right. Since these things, when x is super big, like 1,000,000, these become inconsequential. It's more than 1,000,000 times as big as these things. And then the inputs would be positive on both sides, except that it has a negative coefficient driving it down on both sides. That is huge. All right, let's do another one. Everybody do number 23. And go ahead and hit enter into your group chat. And group 1. What do you have for this?
We got left down and right up.
And can you explain? Why did you say right is up?
Because
This is Valerie. I can try.
Go ahead.
So, I guess if you were to factor the x squared into the 2x to the third, it would be x to the fifth, right?
So if we multiply these in, f of x becomes 2x to the 5th minus x cubed plus x squared. And then this is the leading term, and there's the leading coefficient, and because to the 5th it's odd, so then it's going to work just like all the other odds do, and it's up over here, down over here, as long as the coefficient in front of it is positive, which it is. Alright, awesome. And alright, there was a lot with end behavior. Tell me how you feel. Let's go to the main chat about end behavior. Feel getting comfortable? Feels like, or is it mostly confusing? Tell me where you're at. Alright, we're seeing alright, this is good feedback. Let's stay here a little longer. I was going to run on to the next topic. Alright, but that's very good feedback here. Alright, let's to this one. Number 24. End behavior of that one. Well, actually, before this one is a complicated one. Before we do this one, let me just, based on the feedback, let me give just a real quick summary again. If f of x equals 5x to the 7th, it doesn't matter what comes on after this. My end behavior is going to look like this. Why is the end behavior going to look like this? Because when this is odd, you're going to have a big number, 5 times this big number to the 7th is going to be positive. It's going to be large and positive. When you put this as a negative big number, like negative 1,000, you're going to get a negative number because you're raising it to an odd power. All right, now, all you have to do is focus on the leading dude. If you had f of x equals negative 5x to the 7th plus, it flips this around. This is a reflection across the x-axis. We've done these transformation things. When it was going to be a positive height, it's now a negative height. When it was going to be a negative height, it's now a positive height. And it goes like this. Okay. If that leading coefficient is even, though, then they both go in the same direction. Both up if it's positive, both down if it's negative. All right. So now, let's go back to number 24. And eraser here. Let's copy this thing. Come down here. All right. Do the end behavior of this. What's happening at the far right? What's happening at the far left? When you get your answer, type it into your group chat. Don't hit enter quite yet, though. Go ahead and hit enter. All right, group 1. What's the end behavior?
It would be right down and left up.
And can you add any insight to why that's the case? If you can't, that's okay. It's kind of like, why do you go down on the far right?
Zumari.
Okay.
It's because the x is negative, it's x, negative x to the 7th. X to the 7th means they're going opposite ways because the 7 is odd. And negative means it's, what's the word, reflective.
Very good. All right, we're going to write 2 minus x 7 times. 1, 2, 3, 4, 5, 6, 7 times. That's what f of x is. And if you FOILed this out, I don't want to FOIL this out 7 times. That would take way too long. But I can tell that the highest power, when I multiply all this out, is if I pick the x every time, I'm going to get x to the 7th. And there'll be an odd number of negatives, so it's going to be negative. So the only thing that matters is this leading term right here. And it is odd. So since it's odd, we'd normally want to do up on the far right, down on the far left. But it's also negative, so it reverses. On the far right, instead of going up, it's going to be going down. And on the far left, it'll go up. And so it's exactly like what's stated here. All right, so the end behavior, not a simple idea. All right, those were... Here's a little summary. The end behavior of a polynomial f of x is determined by the degree of f of x and the sign. Now the size of the number doesn't determine the end behavior. Whether it's a 2 or a 200 doesn't matter. But if it's positive or negative, that is huge. It's the sign of the leading coefficient. So these are the two things. The degree, totally, it's just that one term out in front that has the highest degree, and then the sign. If the degree of f of x is even, the end behavior is both up, if it has a positive leading coefficient, or both down, if it has a negative leading coefficient. If the degree of f is odd, then the end behavior is one up and the other down. And if it's negative, it kind of flips its normal role. The normal role is on the right, it's up. Okay, now you can memorize these things, but they'll be a hell of a lot easier to memorize if it makes sense, if you plug in some values and you kind of play around with it enough so that it makes sense. Okay. That's a summary of it all. Y'all, hopefully you're using your OneNote yourself, and so sometimes if I scroll too fast and you can't like write all this down into your notes, you can come back and use OneNote. You also might play around with your screen capture. If you're on a Windows machine, you hold down the Windows button and then the print screen, and then you've copied it, and then you can go into like Microsoft Word or some word processor and do paste, and it'll show up. All right, now finding intercepts. We've already done these before, but we're going to review them. X-intercepts are going to just have some new names. We call them roots or zeros. So here's a function that I drew, kind of a random one, but we already knew this. When you're at a y-intercept, your x-coordinate, opposite letter is 0. 0 over 3up. When you're an x-intercept, your opposite letter, the y-coordinate, is 0. 2 zeros over here, 4 0, 6 0 over here. Now, notice that we have multiple x-intercepts. We would never have multiple y-intercepts, because if it hit the y-axis here and then later hit the y-axis down here, it's not a function. Function has to pass a vertical line test. a vertical line would be hitting our graph more than once. So generally, we can have as many x-intercepts as we want. We have one y-intercept, and that's it. All right. The x-intercepts, since there's multiple of them, and for other reasons as well, they're generally more important than the y-intercept. And we usually really are interested in what are our x-intercepts. What's always true about x-intercepts? The answer is the opposite letter is always 0. The y-intercept, the x is 0. Now, this is also, it's just an observation, but it's also how we find them. If all we have is the equation, and you're asked to find the x-intercept, what do? You substitute 0 for the y and solve the equation. If you're asked to find the y-intercepts, you substitute x equals 0 into the equation and then solve it. So this not only tells us something about the graph, but it tells us how we go about finding them. Alright, and can a function have more than one x-intercept? The answer is yes. Can it have more than one y-intercept? No. Wouldn't pass the vertical line test. So it wouldn't be a function. Polynomials are all functions. And they're going to pass this, so they'll have just one vertical asymptote. Alright, so you're going to be asked to find the x-intercepts. Now, the x-intercept is the harder one. The y-intercept is really easy. If I asked you on number 10a to find the y-intercept, you just substitute the x as 0 and the y is 6. And, it zeroes out everything, and then the y is already by itself. So that's why we don't usually focus on the y-intercept. They're easy. X-intercepts can be harder. All right. Find the x-intercept of this. We just set the opposite letter equal to 0. 0 equals 3x plus 6. We solve this. Subtract 6 from both sides and you get negative 6. Divide by 3. X is negative 2. Now, I don't prefer that you stop there and say you're done. When I ask for an x-intercept or a y-intercept, I want you to give me the answer as a point in space. X is negative 2. The y is 0. Give me both coordinates. Alright, so you do B. Find the x-intercepts of that. Okay, I'm going to set the y to be 0. Now there's two ways I can go about this. It's a quadratic equation. I can add 9 to both sides and take the square root of both sides. Or I can also do this. Factor it. If I factor it, I can tell that x is equal to negative 3 and x is equal to 3 are both solutions. Negative 3 causes this one to be 0. Positive 3 causes the second parenthesis to be 0. So my x-intercepts are negative 3, 0, positive 3, 0. Alright, Now, I might have looked at this and said, oh, it's obvious, x is 3. And I'd have missed the negative 3. So that's why doing this process can be helpful and make sure that you don't overlook something. And, oops, I missed a parenthesis here. Find the x-intercepts of C. I'll give you 30 seconds. Okay, to do this one, find x-intercepts set the opposite letter to be 0. When a bunch of numbers multiply to be 0, the only way they can happen is if one of these numbers is 0. Now the 2 is stuck at 2, it can never be 0. But the x minus 3 will be 0 if the x is 3. Now some people learn to look at it logically that way. Others just learn a format. You might have learned it like you set each one of these to 0. And then you solve the equation. And either way is fine. Whether you were told to set up each as a, when these things are complicated things, then you need to be able to do that. But I like to just look at it logically most of the time, unless it's kind of a complicated expression in there. But then I don't suffice that as my answer. I say, here are my x-intercepts. All of them will cause the y to be 0. Like this. Alright. Now, let's talk in generalities for a minute. What we are doing is we're going to build up a body of knowledge that we'll be able to look at something like y equals x to the 6th plus da 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 da. It's a big old thing. And we'll be able to say, hey, I know what this looks like in general. It looks something like this, because I know it's in behavior. And then in between these, it's got to like hit the x-axis and hit the y-axis at various times. And if I just get those points where it hits the x-axis, hits the y-axis, I've got a lot of information about this. I know where it goes in the long term, and I know something about what's happening in between. Okay, so that's where we're going, and that's why we're focusing on the intercepts. Now, the maximum number of x-intercepts of a polynomial f of x is the same as the degree of the polynomial f of x. All polynomials have exactly one y-intercept. So let's look at these. Let's look at this one. I wrote f of x equals x squared minus 9. If I was to graph this function, its y equals x squared looks like this. But this causes the shift down 9. So it's way down here at negative 9. It's doing this. And what is it doing for x-intercepts? It has 2 x-intercepts. One here, one here. Alright. Now look at its degree is 2. And it has 2 x-intercepts. Now, But the fancy word in here is maximum number of x-intercepts. It might be, let's go to a different color. If f of x is x squared, now that's a second degree polynomial, but it has only one x-intercept. Let me do a different one. F of x equals x squared plus 2. That got shifted up 2. And it has no x-intercepts. So a second degree polynomial might have one x-intercept, might have no x-intercept, but the maximum it can never have is 2 x-intercepts. It can never have 3 x-intercepts. Now, why in the world, how am I so confident that a second degree polynomial can never have 3 x-intercepts? If it had 3 x-intercepts, then all the x-intercepts would be solutions to this equation. Because what does it mean to be an x-intercept? It causes the y to become 0. So you're sitting on the x-axis, height of 0. And if it had 3 solutions, then notice this would FOIL out and become a third degree polynomial. Third degree polynomial can have 3 solutions, but a second degree polynomial can't have more than 2 solutions. Okay. This one is, something like this was in the practice quiz today. This one, if we graph this, we shift it to the right 4, no, left 4. Horizontal shifts go in the opposite direction. And that has one y-intercept over here. Alright, so that's x-intercepts. Very important thing about the maximum number of x-intercepts. The turning points of a polynomial is one less than the degree of the polynomial. Alright, so let's talk about this. The turning points, if your function is going uphill and then turns and goes downhill, that's a turning point. It's going downhill, now it turns and goes uphill. And then it turns and goes back downhill. Those are all turning points. Changing from uphill to downhill or vice versa. From increasing to decreasing, vice versa. Alright, now, f of x equals x squared, that's a parabola. And what does that look like? Is this? And how many turning points does it have? Well, it's a second degree polynomial, and it has one turning point. Now, parabolas can have at most one turning point. Let me describe what would happen if a parabola had 2 turning points. Here's a parabola with 1 turning point. How many zeros does it have? 2. If it had another turning point, it could now have 3 zeros. And then it's not a parabola anymore. It would have had to have, when this, x minus whatever this number, x minus whatever this number, x minus whatever this number, has to be part of the function. Like these three. See, if you had a function like this, third degree polynomial, to graph it, you'd say, I'd find the x-intercepts, and they're going to be at 2, and at 4, and at 5. Those are all x-intercepts. That's the third degree. It needs to have, now we know something about the end behavior of this as well. The end behavior, if you FOILed this out, the leading term would be 7x cubed. And so that's on the far right, it goes up. On the far left, it goes down. Now, we can take that from the x-intercepts, and then we can say the graph looks something like this. We're starting to get a fair amount of information about polynomials now from the end behavior and the x-intercepts. That'll tell us quite a bit. Now notice, third degree polynomial, how many turning points? Maximum number of turning points is 2. But it doesn't even have to have 2. It could have 0. F of x equals x cubed looks like this. And it doesn't have any turning points. But the maximum it can have is 1 less than the degree. Second degree, 1 turning point. Third degree, 2 turning points. All right. That is it for today's lesson, the homework. It's 5.2. And one last reminder again. You've got spring break, so I won't be seeing you for a while. But when you get back, the practice test is due before the next class when we get back. Exam 2 practice test is due on the 22nd at 12:30. And I will stop here. Any questions, comments? Anybody need to talk to me?